Hello, space explorers. For many centuries, we have been familiar with the image of the solar system as a perfect model for planetary systems in the universe. A star at the center, smaller, more rocky planets nearby, and gas giants far away. But the universe always holds surprises. Over the past 20 years, astronomers have discovered odd planetary systems with completely different structures. For example, hot Jupiters, gas giants cooked by the heat of their host star, have left scientists scratching their heads to explain their existence. And today, we will explore together even more strange planets and planetary systems that can make the picture of the universe more complicated than ever. What makes them so special? As always, if you find this video interesting, don't hesitate to take about 5 seconds to leave your comments below. We, the video production team, always appreciate and thank you for all your feedback. Let's get started. Have you ever imagined yourself standing on a distant planet, watching two suns sink into the horizon? This magnificent scene no longer only exists in the Star Wars movie, but has become a reality with Kepler-1/6b, a Tatooine-like planet whose existence has just been confirmed by astronomers. Kepler-1/6b, located 245 light-years away, was discovered by NASA's Kepler Space Telescope in 2011. So how was Kepler-1/6b discovered? The answer lies in NASA's Kepler Space Telescope. Scientists use the solar transit method, which means observing the change in brightness of a star when a planet passes in front of it. In the case of Kepler-1/6b, they noticed the dimming of one of the two stars in the system, even when the other star was not eclipsed. Josh Carter, a member of the research team, confirmed, "This is the first confirmed example of a planet orbiting not one, but two stars." However, after Kepler stopped working, this planet seemed to have disappeared from our sight. But no, Kepler-1/6b is still there, quietly orbiting its two parent stars. And this time, scientists used a different tool to find it, the Haute-Provence Observatory in southern France. With the 193-centimeter telescope at this observatory, astronomers observed and confirmed the existence of Kepler-1/6b, marking a new step forward in finding and researching exoplanets in the solar system. But what makes the Kepler-1/6b so special? This gas giant is comparable in size and mass to our famous solar system cousins, Jupiter and Saturn. However, unlike these two planets, Kepler-1/6b does not have a solid surface for us to set foot on. Instead, it is a giant ball of gas with an extremely cold surface temperature, ranging from -100 to -70 degrees Celsius, -150 to -94 degrees Fahrenheit, equivalent to about 188 Kelvin. Despite its extreme surface temperatures, ranging from -100 to -70 degrees Celsius, Kepler-1/6b lies near the outer edge of the Goldilocks zone, the ideal area around a star where liquid water can exist. This is made even more interesting by knowing that Kepler-1/6b orbits not one but two stars, a binary pair consisting of a K-type star and an M-type star. The planet completes an orbit around the pair every 228 days, roughly the time it takes Venus to orbit the Sun, 0.71 astronomical units. Imagine you are standing on Kepler-1/6b, in your imagination of course, because this is a giant gas planet. You will see two suns dancing in the sky. The larger and hotter K star will shine brightly, with a surface temperature of up to 4,450 Kelvin. Meanwhile, the smaller and cooler M star will emit a soft glow with a temperature of 3,311 Kelvin. The intriguing interaction between these two stars is also extremely interesting. They orbit each other with a period of only 41 days, much faster than the orbital period of Kepler-1/6b. This means that over the course of a year on Kepler-1/6b, you will see these two stars dancing around each other dozens of times. Kepler-1/6b also has another name, more familiar to Star Wars Tatooine fans. The name was given by the Smithsonian Institution as a reference to Luke Skywalker's home planet, which also has two suns in the sky. However, unlike the arid and sandy Tatooine, Kepler-1/6b is a gas giant composed mainly of gas, with a portion of rock and ice. Its mass and radius are comparable to those of Jupiter and Saturn, two gas giants in our solar system. What's even more interesting is that Kepler-1/6b was measured with incredible precision. According to Lawrence Doyle, lead researcher, Kepler-1/6b radius was known to an error of only 0.3%, better than any other known exoplanet at the time, September 2011. The discovery of Kepler-1/6b using ground-based telescopes opens up many new opportunities for studying extrasolar planets. If previously we could only rely on expensive space telescopes like Kepler to search for new planets, now ground-based observatories can also contribute to discovery. Vast universe. Did you know that most stars in our universe are not alone, like the Sun? They exist in binary star systems, even triple stars or more stars. This raises an interesting question. Are there planets orbiting these stars, and could they harbor life? To answer this question, astronomers have developed a new, promising method that allows the detection of exoplanets in binary star systems without the need for expensive space telescopes. This method, called the radial velocity method, is based on measuring small changes in the star's velocity as affected by the gravitational pull of the planets orbiting it. The success of this method has been demonstrated by the rediscovery of Kepler-1/6b. But Kepler-1/6b is not the only case. Of the 2,662 exoplanets discovered by the Kepler Space Telescope, there are still 12 planets orbiting binary stars. But such star systems are said to make up the majority. In 2001, the astronomy world was abuzz with a strange discovery. HD 80606b, a planet with the most unusual orbit ever recorded. Unlike its brothers in space, HD 80606b moves in an extremely long elliptical orbit, sometimes up to 5 million kilometers away from the host star, then rushed back again in just 111 days. This rebellious planet quickly came into the sights of NASA's Spitzer Space Telescope. Leading scientists from MIT, the Space Telescope Science Institute, the University of California at Santa Cruz, and many other institutions began researching HD 80606b. They discovered that despite being the same size as Jupiter, the planet's mass is up to 4 times that, turning it into a true giant. Located 190 light-years from Earth in the Ursa Major constellation, HD 80606b becomes a potential research object, opening new doors for understand the diversity of planetary systems in the universe. Instead of following a circular path around the host star like other planets, 8D 80606b chooses an incredible journey. 110 days leisurely in a strange orbit, then suddenly accelerated, rushing around the host star in just 20 hours, almost grazing its surface before shooting away again. This adventurous journey exposes it to harsh conditions. During the moment of closest approach, this planet receives a huge amount of radiation from the host star, more than 1,000 times the energy that Earth receives from the Sun every day. Julian DeWitt, a researcher in MIT's Department of Earth, Atmospheric and Planetary Sciences, said, "If our Earth were placed in that position, the atmosphere would be blown away, and the surface would melt into magma." By monitoring the planet for more than 85 hours, scientists recorded dramatic temperature variations on its surface during its close approach to its host star. As it hurtled past the star, temperatures on the opposite side of the star spiked to 1,400 Kelvin, about 2,000 degrees Fahrenheit, enough to turn everything to ash. However, it is worth mentioning that less than 10 hours later, the planet's temperature dropped precipitously, becoming invisible before even the Spitzer Space Telescope. Every 111 days, this story repeats itself. Luckily, HD 80606b travels far enough to have time to recover after each close approach to the star. Otherwise, it probably would have burned down a long time ago. Scientists believe that, initially, these hot Jupiters formed very far from their host star, with circular orbits similar to those of Jupiter in our solar system. However, under the influence of gravity from other celestial bodies, their orbits gradually become distorted, pulling them closer to the host star. Every time it gets close to the host star, the giant gravitational force will mold and distort the planet's shape while converting part of the gravitational energy into heat. This process repeats over millions of years, causing the planet's orbit to gradually become more circular, while the distance from the host star also gradually decreases. HD 80606b is believed to be in a transition phase between two states, from an eccentric elliptical orbit to a circular orbit closer to the host star. The process of taming a rebellious planet like HD 80606b is not an overnight thing. The time it takes for its orbit to change from a distorted ellipse to a perfect circle depends on many factors, especially the flexibility of the planet. Imagine you are repeatedly squeezing a rubber ball. The softer the ball, the easier it is to deform and the greater the heat generated. Likewise, flexible planets are better able to convert gravitational energy into heat, helping the orbital rounding process happen more quickly. Based on what we know about gas giant planets in the solar system, scientists estimate this process could take hundreds of millions of years. However, new observations from the Spitzer Space Telescope have brought a big surprise. The planet is not as flexible as scientists predicted. This means that the planet cannot quickly switch to a circular orbit and can even maintain its anomalous elliptical orbit for another 10 billion years, or even longer. This discovery makes DeWitt and his colleagues question previous hypotheses about the formation of hot Jupiters. If HD 80606b cannot tame its orbit in a reasonable amount of time, have we misjudged the movement mechanism of these planets? There may be other mechanisms at play. For example, gas giant planets form close to their host star or move smoothly inward with the help of planet-forming disks. Not only did scientists stop at discovering the strange orbit of HD 80606b, but they also went further in learning about this rebellious planet. For the first time in history, they have calculated the rotation speed of an exoplanet. The results were surprising. It took up to 90 hours to complete one rotation around its axis, twice as long as previous predictions. This means that a day on HD 80606b is nearly 4 days long on Earth. This planet is almost completely opposite to Earth. It is a gas giant orbiting an eccentric star in a binary system and experiencing a change in brightness of more than 800 times each orbital period. Obviously, this is not the ideal place to look for life, but these unique characteristics make it a great laboratory for atmospheric researchers. In November 2007, a team of astronomers led by Greg Laughlin, Lick Observatory, UCSC, made the astonishing discovery of HD 80606b. Using the infrared array camera on NASA's Spitzer Space Telescope, they closely tracked the planet's adventurous journey as it approached its host star. What they observed really made the scientific community wide-eyed. If we could send a weather forecast to someone special, it would probably look like this. Hello viewers, we have just had several weeks of relatively stable temperatures above 80 degrees Celsius. However, a record heat wave is approaching. Next Friday, morning temperatures are expected to rise to around 1,000 degrees Celsius, and by early afternoon, you should seek shelter as temperatures will reach over 2,200 degrees Celsius. The Spitzer research team knew in advance that HD 80606b would experience a terrible sunburn every time it approached its host star. However, they did not expect that they would be lucky enough to witness a rare phenomenon. This planet disappeared from observation for 1.7 hours just before reaching its closest point to the star. This unexpected solar eclipse phenomenon not only brings beautiful images, it also helps scientists confirm the mass of HD 80606b, 4.2 times that of Jupiter, and the orbit's tilt angle compared to Earth, 90 degrees. Of the hundreds of hot Jupiters that have been discovered, HD 80606b is the only one with such an eccentric orbit. The eccentricity of this orbit is up to 0.93, which means that the distance between HD 80606b and its host star ranges from 0.03 to 0.85 times the Earth-Sun distance. This leads to extreme temperature and light changes on the planet's surface. When closest to the star HD HD8606b receives 800 times more light and heat than when furthest away, turning it into a hot hell. For astronomy lovers, HD80606, the host star of this anomalous planet, is also an attractive observation target. With an apparent magnitude of 9, you can easily admire this star through large binoculars or an amateur telescope. Located 190 light-years away in the constellation Ursa Major, HD80606 has a mass and brightness similar to the Sun, but it belongs to spectral type G5, meaning its surface temperature is slightly lower than that of the solar system's central star. However, the most interesting thing is that HD80606 is not alone. It has a near-twin companion only about 1,000 astronomical units AU away, equivalent to 25 times the distance from the Sun to Pluto. It is the gravitational force from this companion star that strongly impacts HD80606b, creating the planet's extremely flat and strange elliptical orbit. This mechanism, known as the Kozai mechanism, turns HD80606b into one of the most anomalous planets known. However, the strange planets in the universe don't stop there. Astronomers have discovered TOI-178, another planetary system that also carries with it equally unique mysteries. TOI-178 is actually the abbreviation for TESS Object of Interest, and 178 is simply the 178th star on the list discovered by the TESS Transiting Exoplanet Survey satellite. So how does TESS do it? Imagine you are observing a streetlight from afar. If a moth flies in front of the lamp, you will see that the light is slightly dimmed. TESS works on the same principle, but instead of moths, it looks for microscopic eclipses caused by planets as they pass in front of their host star. This phenomenon is called transit. However, we are not always lucky enough to observe a planet's transit. This only happens when we look at the star system from a vantage point, just like you can only see a moth blocking a light if you stand in the right position. But once the transit is observed, astronomers can glean a lot of valuable information. By measuring the time between transits, they were able to calculate the planet's orbital period, or, in other words, the length of a year on that planet. In addition, the degree to which the star's brightness decreases also reveals the size of the planet. The larger the planet, the more light it obscures. After analyzing data from the TESS telescope, scientists have found 6 planets orbiting the star TOI-178. What's amazing is that the 5 outer planets move in an extremely rare orbital resonance pattern. Imagine a symphony orchestra, where each instrument plays a separate note but all blend together to create a harmonious piece of music. Similarly, each planet in the TOI-178 system has its own orbital period, equivalent to a year, on that planet, but they are related to each other in a proportional manner. Simple and gorgeous. More specifically, the orbital periods of these planets, calculated in days on Earth, are TOI-178b, 1.91 days, TO-178c, 3.24 days, TO-178d, 6.56 days, TO-178, 9.96 days, TO-178, 15.23 days, TO-178g, 20.71 days. If you're observant, you'll notice something interesting. Planet D's period is almost twice that of Planet C's. Planet E's period is 3 times that of Planet C's, and so on. Continue with planets F and G. More specifically, for every 18 rotations of planet G, the farthest, planet F will rotate 12 times, planet E will rotate 9 times, planet D will rotate 6 times, and planet C will rotate 4 times. What does this mean? This means that after a certain period of time, these planets will return to a relatively similar position in their orbits. Imagine a group of dancers performing complex dance moves, but always returning to the starting position after a certain number of beats. That's exactly what's going on in the TOI-178 systems. The TOI-178 planetary systems are not the only cases of this strange orbital resonance dance. In fact, TOI-178 are the 5th planetary system to have this phenomenon. But the interesting thing is that these planets do not move independently. They are like dancers in a group dance, influenced by each other's gravity. When a planet tries to overtake and move faster, the outer planet exerts an opposing pull, and vice versa. With the 5 outer planets moving in such an orbital resonance, any small disturbance can have big consequences. If a planet is deviated from its orbit, even slightly, the entire system will be disrupted. The other planets will no longer move in harmonious rhythm, and this unique resonance structure will no longer exist. This also means that the TOI-178 systems may have undergone a relatively peaceful evolution, unaffected by major cosmic events. If another large planet strayed into this system and exerted its gravitational pull on the other planets, the resonance chain could have been broken long ago. The movements also tell us the size of the planets. They are all larger than Earth but smaller than Neptune, with sizes B equals 1.18, C 0.71, D equals 2.64, E equals 2.17, F equals 2.38, and G, respectively, equals 2.1 times Earth. This puts them in the super-Earth and mini-Neptune groups. However, it is worth noting that the arrangement of these planets is not the same as in our solar system. While our smaller planets like Mercury, Venus, Earth, and Mars lie closer to the Sun, giant planets like Jupiter and Saturn lie further away. In TOI-178, this arrangement is reversed, creating a unique and different structure. But the story doesn't stop there. Astronomers also use another technique called radial velocimetry to determine the masses of these planets. By observing the star's wobble caused by the planet's gravity, they were able to calculate the mass of each planet. When scientists calculated the density of these planets by dividing mass by volume, they discovered an interesting disturbance. The Earth's density is considered a reference point, about 5.5 grams per cubic centimeter, equivalent to 5.5 times the density of water. Meanwhile, the density of planets in the TOI-178 systems is very diverse and not in a certain order. Specifically, the 2 planets closest to the star have densities equivalent to those of Earth. However, the 3rd planet has a significantly lower density, only 15% of Earth's density. Meanwhile, the 4th planet has a higher density, nearly 40% of Earth's density. This difference continues with the remaining 2 planets, where their densities are 58% and 19% of Earth's density, respectively. So, what does this mean? The density of a planet is an important indicator that helps us understand its composition. Rocky planets often have high densities, close to or greater than Earth's density, while gas giants have much lower densities. In our solar system, rocky planets are often closer to the Sun, while gas giants are farther away. However, the TOI-178 systems are completely different, with a mix of high and low density planets. This raises a big question for scientists. How could a planetary system form with such a chaotic density structure? Are there other factors that influence planet formation that we don't know about? Obviously, TOI-178 still contain many mysteries waiting to be discovered. The truth is, we have only begun to explore a small part of the universe. There are likely billions of other planetary systems out there, each with its own distinct and unique characteristics. Finding systems like TOI-178 just 200 light-years away suggests that this diversity may exist right in our neighbors. So, what does this mean for us? Perhaps we need to change the way we perceive our place in the universe. Instead of considering the solar system as the norm, we should broaden our horizons and embrace the rich diversity of the universe. Maybe it is the strangeness of the solar system that has created conditions for life to develop on Earth. Have you ever thought about there being planets that don't belong to any stars, wandering alone in the universe? They are called wandering planets, nomad planets, or rogue planets, and they are the real winners in the galactic game. While we debate whether Pluto is a planet or not, these wandering planets are freely exploring the universe, untethered to any star. They have no day or night, no years, only an endless journey in the cold darkness of space. What's amazing is that the number of these planets may far exceed what we imagine. Estimates suggest that for every planet orbiting a star, there could be between 1 and 10 wandering planets. With hundreds of billions of stars in the Milky Way, this means there could be trillions of rogue planets in our galaxy. In fact, they are difficult to detect for two main reasons: their small size and low brightness. Imagine trying to find a small pebble on a large beach at night. It's an almost impossible task. Likewise, wandering planets are very small compared to stars, and they do not emit their own light. They only emit a faint bit of infrared light due to their internal temperature, making them almost invisible in the vastness of space. Because of this combination of small size and low luminosity, identifying a wandering planet is a major challenge for astronomers. To date, only a few dozen rogue planets have been discovered, and most of them are still the subject of debate and need further confirmation. So, how can scientists find these tiny pebbles in the vast cosmic beach? They used a variety of methods, including observing the influence of the wandering planet's gravity on light from distant stars, or looking for tiny signs of infrared emission. A prime example of these incredible discoveries is OTS 4.4, a rogue planet 11 times the mass of Jupiter, 554 light-years away. However, is it really a wandering planet or a brown dwarf? Brown dwarfs are half-star, half-planet objects, too large to be considered planets but too small to sustain nuclear fusion like a true star. OTS 4.4's mass lies on the boundary between a planet and a brown dwarf, making its classification difficult. Imagine a planet 11 times more massive than Jupiter, floating freely in space. With such a huge size and mass, OTS 4.4s could cause terrible collisions if it encountered another planet on its path. The consequence of such a collision would be the complete destruction of the smaller planet, while OTS 4.4s continues its journey as if nothing had happened. There are not only giant wandering planets like OTS 4.4s, but also smaller planets about the size of Earth, wandering in the vast universe. A good example is OGLE 2016b LG1928, discovered in late 2020. This is considered a special, rogue exoplanet in many ways, not only because it does not belong to any planetary system, but also because of its small size. In fact, this is the smallest rogue planet ever discovered, while most other rogue planets are similar in size or larger than Jupiter. Finding small, wandering planets in the vast universe is no small challenge. However, astronomers succeeded thanks to a sophisticated technique called gravitational microlensing. What is gravitational microlensing? Imagine a wandering planet passing in front of a very distant star. The planet's gravity will bend light from the star like a giant lens. This change, although very small, can be detected by sensitive telescopes, thereby revealing the presence of the wandering planet. In the case of OGLE 2016b LG1928, the light distortion lasted only 41 minutes, indicating that this is a very small planet. Despite the paucity of observations, astronomers are fairly certain that rogue planets exist. That's because, in simulations of solar system formation, lots of planets formed instead of orbiting the star. They were kicked out of their homes as children to live a life on the streets, among the stars. The really wild thing about rogue planets is that they could be homes for life. These planets are thought to range in size from tiny specks of dust like Pluto to giants larger than Jupiter. Even though they don't have stars to warm them up, they can still retain some of the heat from their formation. Try to imagine the Earth separated from the Sun. Although the surface will become cold, geological activities such as volcanoes and hot springs will continue, generating heat. And where there is heat, there is the possibility of liquid water, an important element for life. So, what forms of life could exist on these wandering planets? What will they look like? Are they similar to life on Earth? These are challenging questions that scientists are trying to answer. Hello, future space explorers and space lovers. Our 30-minute journey to explore the strangest planets has come to an end. I hope you have had enjoyable moments while browsing through stories about the volatile hot Jupiter HD 80606b and the dancing planetary system T OI 178. The universe always holds surprises and wonders, and each planet has its own story to tell. Let's continue to explore these mysteries with Space 30 Minutes in the next videos. Don't forget to like, share, and especially subscribe to the channel so you don't miss any new and interesting information about the universe. If you have a favorite exoplanet, please share it with us in the comments section below. Thank you for accompanying me for 30 minutes. Wishing you always happiness and constantly discovering the wonders of the universe. See you on your next adventure.